Good day, everyone. I am Olatunji Mishri, and today I'll be presenting my work, which is on weakly supervised learning via multilateral decoder branching for tool segmentation during robot-assisted cardiovascular catheterization. So here is the content of my presentation. And as we know, cardiovascular disease is actually one of the leading cause of death. And then it's recently receiving a whole lot of attention. So in our research, we have actually been looking on how to develop systems, intelligent systems that can be used for the diagnosis and as well as treatment of cardiovascular diseases. So typically, conventionally, we know that this requires a lot of manual tasks whereby surgeon would have to cannulate the vessels using endovascular tools such as guide wire and catheter, and then manually they have to be exposed to the hazard in the operational room, such as the exposure to radiation, and also they would have to face some orthopedic issues because they have to stand glaring their heads on the screen in order to track the surgical tools during the procedure. So to reduce these exposure issues, there has been developments in the areas of robotic systems, using the robotic system to replace the surgeon in the operational room, whereby the surgeons will be outside of the cockpit and manipulating such tools remotely. So, but then there are still some challenges. For example, of course, the exposure has been able to reduce, at least for surgeons, but then they face the loss of feedback, whereby they cannot really make judgments about how the tool vessel interaction is going on during the procedures. So for this, in this study, we're actually focusing on how to automate some of the tasks, especially in the area of visualization, and then we're coming up with some imaging strategies or techniques that can be used to segment and as well as track tool pixels in angiograms during robotic catheterization. So there has been some level of research developments in this area. For example, imaging techniques such as deep learning has been used for pixel level tool segmentation in different surgical procedures, but for cardiovascular interventions, there has been only very minimal efforts. And especially in the year 2000 to 2023, we have seen new developments in using some new learning-based strategies, such as the weakly supervised learning. For example, Lu et al. Proposed the concept of dual decoder branching for medical image segmentation, which happens to be one of the main motivation for this study. So in this work, we're actually using the point-based labeling for annotating, for weak annotation of images that are obtained during robotic catheterization, and then using that to train a machine learning or a deep learning model using weakly supervised strategy. So this can actually reduce the burdens that the surgeon would have to be faced with when trying to annotate a huge lot of data sets for fully supervised learning method. So of course, this is to aid the visualization and as well as automate some of the tasks during the robotic characterization process. And our motivation is that this can actually enhance surgeon-robot collaboration during the procedure. For example, some tasks such as tool segmentation and tracking analytics can actually be automated during the procedure. So in our proposed method, we have actually taken an assumption that we have data instances that are drawn from a Gaussian mixture model, and then we're trying to see how we can actually predict what the labels or classes of these pixels could be. So pixel can actually be classified into two different classes in these studies, and that can be as a foreground, which happens to be one of the surgical tools, such as the endovascular guide wire or catheter that are used during endovascular procedures, or it can be background, which actually the background of such or in such angiograms. So for this, we are actually proposing a concept of weakly supervised segmentation technique, which is going to be based on multilateral decoder branching, as opposed to one of our previous studies where we actually have multilateral encoders in the model. Here we have multiple decoders that actually works in parallel, and then we take an ensemble of the output from all those decoders in order to be able to predict what the eventual or the actual class of the pixel is going to be. So in this, we have three decoders. Of course, we have experiment for two also, but then here we have three decoders whereby one can serve as a main decoder, and then the other two are going to be auxiliary decoders. For the main decoder, we're going to train that with a fully supervised method using cross entropy, and then we use that to generate pseudo labels that are used to train the auxiliary decoders. So this involves a kind of pairwise training strategy with shared consistency. In the first lap, we actually have to minimize the function that is given on the slide. And then this includes both the supervised component and as well as the unsupervised, I mean, the weekly supervised component. And also we actually have to combine all this loss training, organization training process using a regulated shared consistency approach, whereby we have a consistency term that is used to ensure that we reduce the perturbations that exist amongst all the several decoders. So typically, this actually restricts it actually reduces the mislabeling in the model, and as well as we're able to have a model that can actually use weekly annotated images to determine which of the pixels actually belongs to the true pixel or for the background pixel. So we have been able to validate the model also. We use three different kinds of data sets. This actually includes two proprietary angiogram data sets that are obtained in-house from animal experiments, which include an experiment in a pig study and another experiment in a rabbit study, as shown on the slide. And the third data set is a public data set that was obtained on the internet, and this is from the UCL in London. So we have actually validated the model on these three data sets. So as shown on the slide, this is a typical view of how the labels, the labels that are created or the supervision signals that are created looks like. That is, we have a discontinued annotation for all the tool pixels in the angiogram, and then this will actually use to train the proposed weekly supervised learning model. We have implemented the model using a TensorFlow Keras framework on the Linux server, and then train on an NVIDIA RTX 8000 GPU. And also, these are the training parameters that are shown on the slide. So in order to ensure consistency amongst all the image from the different sources, we actually have to resize all our images to a 56 by 256 pixels and all partially annotated as shown on the right side of the slide. So typically, we actually have a very good performance for the proposed weekly supervised model. For example, on the rabbit dataset, we have an MIOU, that is mean intersection over union, of more than 70%. And as well as for the pig dataset, we have kind of a bit low performance, which is lower than that of the rabbit dataset, which is 67%. And as well for the phantom dataset, we actually have a better performance, which is more than 84%, showing that this model can actually work for different kind of data sets. And similarly, these performances are very close to what we obtained from the fully supervised models. And as you can see, it has very high area under curve for the three different data sets, and as well as their misclassification rates are quite low. Also, we had an evaluation studies by comparing the proposed weekly supervised method to some of the existing weekly supervised method. Aside the fact that it has a very close mean margin with the fully supervised model, it also has better performance than some of the existing weekly supervised methods, such as the entropy minimization technique, the total variation technique, and using the commonly used Mumford-Shah approach. So also, the proposed method has a high mean percentage difference when compared to the fully supervised model. Also, we carried out application studies and were able to confirm that the proposed model has the best performance, and that was obtained by using the multilateral decoders with 3 decoders run with a consistency value or consistency term of 0.5. And then when we change the loss function to using an hybrid function, which was earlier proposed in one of our earlier studies, it also has a better performance compared to when we change the variation, for example, using the lateral decoders to just 2 decoders, or changing or varying the consistency value as shown on the plots at the lower left of the slide. Similarly, we also changed the backbone of the network by using some of the existing backbones, and we found that by using a multilateral branch encoder with the multilateral branch decoder has the best performance, which is even more than what we have when we use the UNet backbone. Lastly, we deployed the model for robots-assisted characterization for real-time segmentation during the procedure. And as you can see in the video shown on the slide, the model actually has very good performance. For example, we use this study for guide wire, which is shown on this video, It has an MIOU of more than 65% for a real-time procedure, and as well as the execution time is quite low at 35 milliseconds with a very high connectivity, which shows that the model can actually be deployed for real-time or online robot-assisted characterization trials. So in conclusion, we have been able to propose an approach where we can automate some of the visual tasks during robotic characterization using multiple backbones, which show how the model can actually work for weekly supervised annotations or annotated images. And as well as this was validated on 3 different data sets. So we hope that this can actually aid tasks such as visual analysis or visualization during real-time robotic characterization, and in fact, hoping that it can also enhance surgical scene analytics in real time during robot-assisted characterization. In the future, we're looking for a way to improve the connectivity of the segmented outputs, and as well as seeing how to ensure that we can have a model that has faster response, faster segmentation time during the procedure. Thank you.